Hello everyone from Math 2000, Linear Algebra. It's Professor Winson here again with a video on your Zybooks section 6.4 titled 4 Fundamental Subspaces. Now these are going to be 4 fundamental subspaces of some Euclidean space, some Euclidean coordinate space, Rn, Rm, that are related to a certain matrix. So again, every vector space has 4 subspaces associated with the vector space that are considered the fundamental subspaces of that vector space. These subspaces are called fundamental because the solution of the system of linear equations, say some matrix A times some column vector X equals a column vector B, and the existence and uniqueness conditions for a solution can be discussed exclusively using these subspaces that we're going to be introduced to. Now these subspaces are the column space, the null space, sometimes referred to as the kernel, and then the row space and left null space. Right. So the first of these spaces is the column space of a matrix. Alright, so the column space of a matrix A, which is some m by n matrix with real entries, is denoted by col of A. So this is the column space of A, and it's this set. The column space of A is the set of all vectors from Rm that are just you take matrix A and multiply it by some vector from Rn, and you'll get a vector from Rm, and that set of vectors from Rm, all the possible products of A times a vector from Rn, will make up what's called the column space of A. So the product of an m by n matrix A and a vector from Rn, can be written as follows, and so on. So you've seen this, right? When you take a m by n matrix, multiply by an n by 1 column matrix, you can really express this product as a multiple of the columns, or a linear combination of the columns of the matrix, right? We have x1 times column 1 plus x2 times column 2 plus x3 times column 3, etc. Alright, so any product of a matrix and a column vector can be expressed simply as a linear combination of the columns of that matrix. So another way to say what the column space of a matrix is, if A is a matrix with these n columns here, and all of these columns are from Rm, right, then the column space of A is simply the span of these columns of A, the span of the column vectors of A, thus the name column space. So remember what the span of a set of vectors was, right? The span of a set of vectors was all linear combinations of those vectors. So the column space of a matrix is just the set of all linear combinations of the column vectors of that matrix, right? The columns of that matrix. And we could prove this by showing that it's non-empty and closed under addition, closed under scalar multiplication. You could show very easily that if A is some m by n matrix, then the column space of A is a subspace of Rm. Right? Remember, this was the vector space with vectors with m real number components. Right? Because all the columns of A would have m components, and any linear combination of those would also have m components, right? So the column space of an m by n matrix is a vector space, and it's a subspace of Rm. Again, very easy to show that, so that, notice they don't even have the proof for it here because it's very simple. And then, just like we'd seen in previous sections earlier in chapter 6, to find a basis for some vector space that's defined by a matrix like this, right? So to find a basis for the column space of matrix A, just put A in reduced echelon form, and then the pivot columns of the reduced echelon form will correspond to the linearly independent columns from the original matrix. And those linearly independent columns will form a minimal spanning set of the column space of A, or a basis for the column space of A. Okay. So they give an example here, which I'll do on some paper. All right, so you're seeing the matrix A here that was in that activity. When they're asking for, hey, what's the column space of A, right? This COL of A. Well, the column space of A is simply the span of the set of the column vectors of matrix A. So the vector, 1, negative 1, the vector 5, negative 6, and the vector 8, 1. Okay. Now, this is a totally valid description of the column space of A. Every vector in the column space is some linear combination of these three vectors. Right. And again, all these are vectors from R2, so this is a subspace of R2. Right. Now, we're going to be asked to also find, a basis for this column space. So, you might think, oh, well, aren't just these three vectors a basis? No, that's not the case here. Remember, if the number of vectors is greater than the number of components in each vector, then they won't be independent. So so this can't form a basis, right? So this set with the three columns, those three column vectors, this is not a basis for the column space of A. And again, the reason for that is these vectors would not be independent. There are more vectors than there are components. So these would be a dependent set of vectors. And if you recall, a basis for a vector space was a set of vectors that was independent and also spanned the space. Now again, these obviously span the space by definition of span, but they're not independent. So we're going to cut this down. That means, one of these, probably, maybe even two of them, I'm going to say one of them, but one of these, at least one of these, isn't necessary. One of these vectors should be able to be written as a linear combination of the others. So find a basis. Okay, so I put this into reduced row echelon form, which, there's only 2 rows here, so probably wouldn't take that long to do by hand. But I'm going to call this A prime, and just so you know it's not the same matrix, or you could call it R or something. I'll just have the calculator do it for me real quick, so I'll come back when I have that. Okay, so hopefully you've seen me do an entry of matrices in the calculator plenty to know where this came from. But my calculator just popped up right in the reduced row echelon form of this matrix. has a first column of 1, 0, second column 0, 1, third column 53, -9. And then to find your a basis for this column space, you look for the pivot columns, right, where these leading ones are. So this first column has a leading one. That means that the first column of the original matrix will be part of my basis. The second column also has one of these leading ones, right? So that means the second column of my original matrix will be part of this basis, and those two vectors would be independent. The third column is not a pivot column in the reduced echelon form, meaning when I say these two are independent, this third one, this vector 8, 1, should be able to be written as a linear combination of these first two. So it's really unnecessary. I don't need it when I talk about forming the column space. Alright, so a basis for the column space. So all this means is that the column space, instead of the span of all three of those vectors, I could say that the column space is just the span of the set with those first two, right? The -1, 1, 1, -1, and the 5, -6. And these are independent. And these are independent vectors, and they span the space. So we also have that the set with these two vectors in it is a basis, right? The most basic building blocks of the column space of that matrix. All right, so you got both these things now. And we've also talked about dimension before. Remember the dimension of a vector space, right? This column space is just the number of vectors that are in a basis for that space. So we'd also be able to say this, that the dimension of the column space of A, this will be given there's going to be a word for this later called the rank, but that's in the next section. But just know that this is going to be called the rank of A in a little bit. Would be 2. This would be a two-dimensional vector space. And after all that reduced echelon form and looking for pivot columns, we can say all three of these things now. Alright, that the column space is the span of just the set of these two vectors. So the set of these two vectors is a basis for that space. That means that every vector in the space can be written as a linear combination of these two, and these two are independent. And because there's only two of them here, the dimension of the column space is 2. Yeah, so you've already kind of seen this before, though, right? We just didn't call things column space. But where I wanted to figure out a minimal spanning set for a larger set of vectors, right? You took those and made them the columns of a matrix, put it in reduced echelon form, and then found the pivot columns, and those pivot columns correspond to a basis, a set of independent vectors, a minimal spanning set for the vector space. Alright, so back here, and they go through all that here as well. Then you're asked to do the same here. Now this one, they're giving you the reduced echelon form of A. And look at the first column and the third column are the pivot columns, meaning the first column vector and the third column vector form a basis for the column space of A. Right? And again, the column space is the span of these 4 column vectors. But apparently I don't need 2 of them. I only need the first and the third one to make the same space. Right? Now, true or false, a basis for the column space of A is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, the pivot columns correspond to the basis vectors, but they themselves are not the basis vectors for the column space, so that's false. Saying now here the column space of A is equal to the span of, negative 2, 1, 1 was that first column vector, and 0, 1, negative 1 was the third one. Again, those correspond to the pivot column, so yes, the span of all four of these is equivalent to the span of just these two, right? Based on our seeing the result of the reduced echelon form and looking for the pivot columns. So this is true. All right. Now I said earlier, when you multiply an m by n matrix by some n by 1 column vector, you get an m by 1 column vector, and multiplying a matrix by a column just gives you a vector from the column space of the matrix. So that leads us to this statement here, saying that if A is some m by n matrix, a solution to the system of linear equations, A times x equals b for some b in Rm, there will be a solution to this if and only if this vector b is in the column space of A. Hopefully that all makes sense based on the previous readings. So then the question here is, let A be this matrix, 2 by 2 matrix. And the question is B is this vector with the components 24 and 2 in the column space of A? Alright, so I'll write this one out as well. So here's the matrix given in the example. And then they're asking, is this vector 24, 2, in the column space of A? Well, what is the column space of A? Remember, the column space of A is the span of the set with the column vectors of A, with the vector negative 8, 6 and the vector negative 10, 5. Alright, and this would be a subspace of R2 again, right? All these vectors here have two components. So another way to ask this question would be, is B a linear combination of, these two vectors? Okay. Same question. All right, so we're solving this system. x1 times negative 8, 6 plus x2 times negative 10, 5. Is there an x1 and x2 such that this is equal to the vector 24, 2? Right. And you've seen this plenty. Right? This can be expressed as a system, as a matrix equation like this, where you have your matrix A, with these column vectors as the columns, multiplied by these, this variable matrix with the x1 and x2, right, with these weights of the linear combination here. And when is that equal to the vector, 24, 2? Right. Yeah. Now you could do this a few ways, right? This is a square matrix, so this will have a solution if you can find an inverse, if that's possible. Well, the determinant is not 0, right? The determinant would be negative 40 plus 60, so 20, and then you could find the inverse and all that, find the solution. So the answer is yes. The determinant's not 0. The answer is yes. But let's find the solution. I'm not going to do the inverse here. I'm just going to do what we normally do and write an augmented matrix for the system. Alright, so you have your coefficient matrix, the A on the left side, little bar where the equals are, and then the B on the other side. And then put this into reduced row echelon form. Now I'm looking at the page from the example. This has already been done. You can have the calculator do it, or do it by hand, do some elementary row operations. It's only 2 rows, it wouldn't be that hard to do, but just to save time, I'll jump to what they have here. So in reduced row echelon form, we're seeing a solution. x1 equals 7 and x2 equals -8. And you can double check this, is 7 times that first column vector from matrix A, the -8, 6, is that -8 times the second column vector, right? Is that equal to that vector B, that 24, 2? And it is. All right, you got -56 plus 80 would be 24, and 42 minus 40 would be 2. It works perfectly. So that means that this vector 24, 2 is a linear combination of these column vectors of matrix A. Right. So that means that 24, 2 is in the column space of A. Right. So after all this, we're going to say finally, the vector 24, 2 does belong to the little epsilon symbol, meaning belonging to, I'm sure you've seen that by now, the column space of A. In there. Good. So again, all things, most things, right, we've come across end up boiling down to solving some system or putting some matrix into a reduced echelon form. We're doing that a lot. Okay, so back to the page. Yeah, so it is in the column space. All right, so again here, here's a matrix A. Now these are vectors from R3, right? Every column has 3 components. So the column space of this matrix, the span of these 3 vectors, would be a subspace of R3. And they're asking the same question as earlier. Is this vector B in the column space of A? Right. Very easy to tell. Again, you're just setting up this system, and I'll just pull up a calculator and make an augmented matrix for that particular system. All right. If I were to set up I'll go second matrix, over to edit. Now, if I were setting up a system where this was the this A was the coefficient matrix, and then you had times some vector x equals b, the augmented matrix for that system would be a 3 by 4. So back on the calculator here, right? A 3 by 4 matrix, and then you got 5, -2, 1 across the top, and then for this first vector B, the first component's 3. And then 4, -4, -8, and then for that first part, the second component of B is 2. And then the third row would have -1, 1, 2, and the third component of that vector B in part 1 is -3. And then I already put the last thing I entered was put something in row reduced echelon form, reduced row echelon form, so I'm just going to re-enter that. And that's just 1 1/3, 1 2/3, 3 2/3. But you're seeing how the bottom has a 0 equals 1 situation. Right. You see how the bottom row is 0 0 0 1, meaning again 0 equals 1, which is false. That can't happen. So that tells me that this vector 3 2 -3 is not in the column space of A, meaning that 3 2 -3 cannot be written as a linear combination of these 3 vectors. the 5, 4, negative 1, negative 2, negative 4, 1, and 1, negative 8, 2. Okay. Very easy. All right, and then you would do something similar for this. Just change the 3, 2, and negative 3 in the matrix in the calculator there to 1, 0, and 0, and then do it again. Put it in reduced echelon form, and see if there's a solution or not. All right. So here in the challenge activity, you're asked to several questions about the column space of a matrix. So this first one is find a basis for the column space of this 2 by 2 matrix, right? The span of negative 2, 8 and 2, 4. Now negative 2, 8 and 2, 4, there's only 2 vectors here, 2 column vectors. Remember, 2 vectors are independent if they're not scalar multiples of each other, and these are not. So these are already independent vectors, so these do form a basis for the column space. Also, if you were to take this 2 by 2 matrix and put it into reduced echelon form, it would just be the 2 by 2 identity matrix. So each column is a pivot column. So each column vector here is part of a basis for the column space. So negative 2, 8 and 2, 4. Very simple, that one. Okay. Next. See what the next level looks like. Alright, look, see here how they ask us again to find a basis for the column space of this matrix. Now, it's another 2 by 2, but this time, 6, negative 4 and negative 12, 8, the columns are not independent. They are scalar multiples of each other, right? If I just multiply 6, negative 4, multiply these by negative 2, I'll get this second column. So this second column is not needed. Or if you were to put this into reduced echelon form, the only column that would be a pivot column would be the first column. So just this one column vector is necessary to form a basis for the column space of A. Alright, so the column space of this matrix is just, the span of one vector, every multiple of 6, negative 4. Very, very easy with the 2 by 2s. Then you're asked to find the dimension of the column space. Now look at this matrix here. It's already in reduced echelon form. So this first column and this last column, the pivot columns, are the basis, a basis for the column space. So 1, 0, 0 and 0, 1, 0 form a basis for the column space of this 3 by 5 matrix. So that's only 2 vectors, 2 columns, right, in the basis. So the dimension of the column space is 2. And I'll leave the last one to you. And it's probably asking for... Now, you can't see my options here, but you have choices here. What is formed by the column space? Remember, there's the 0 vector is one of the options. Again, you're not able to see them in the recording for some reason. But I've got the 0 vector. Well, that's just when you have a dimension of 0. A line through the origin was a space with a dimension of 1. A plane through the origin was a space with a dimension of 2. And all of R3 is one option which has dimension 3. So, just pay attention. So what would be the dimension of the column space, and then what kind of a space is that? Is it a single point, right? Just the 0 vector is 0 dimension. Is it a line, which has 1 dimension? Is it a plane, which has 2 dimensions? Or is it 3D space, 3-dimensional space? All right, so that was the column space of a matrix. The next major one, one of these 4 fundamental spaces, is called the null space of a matrix. Now the null space is also referred to as the kernel. I'll write that down when I go to some paper. Just in case you're watching other videos or looking up other stuff online, if you come across the word kernel, Kernel, that means null space. It's another word for it. So the null space of an m by n matrix is the set of all vectors from Rn that would make it equal to the 0 vector when you multiply. All right, so it's all the vectors that when you multiply that vector by a on the left, you get the 0 vector. That's the null space. And the reason this is called null, null is usually for 0, nothing, right? So it's all the vectors that make turn this matrix into null, into 0, the 0 vector. Now the null space of a matrix is never empty. The 0 vector always is in the null space. Any matrix times the 0 vector will be the 0 vector again. So the 0 vector is one of these vectors. The 0 vector will be in the null space of any matrix. And the null space of a matrix, of an m by n matrix, will be a subspace of Rn. Because again, the vectors that are in here, the vectors that are in the null space of A, are vectors from Rn, not Rm. Alright, and then let's read this stuff here. Performing elementary row operations on A does not change the null space of A. Alright, so any vectors that make A equal 0 when you multiply will also make any row equivalent matrix equal 0. Alright, it's just going back to solving systems. So therefore, if matrices A and B are row equivalent, the null space of A is exactly the same as the null space of B. And they show you, and you can read through this proof here. Now in this proof, they make use of elementary matrices, and we didn't discuss that. We did not cover elementary matrices, so you don't have to really read this proof. Just know this fact, right? That if A and B are row equivalent, then their null spaces will be the same. So for instance, we're asked here to find the null space of this matrix. Now this was actually the matrix we were given earlier, and when we were asked to find a basis for the column space. Again, there are 4 fundamental spaces that are going to be related to every matrix that we're coming across. So this is now the null space. So I'll go to a piece of paper for this one as well. Okay, so here's the matrix given to us in this example. And we're asked to find the null space. And again, I mentioned this is another word that is used in place of the null space sometimes, the kernel. So find the null space or the kernel of this matrix. So again, remember what this is. The null space of a matrix. So just null of A like this. It's made up of all the vectors. So say these vectors called X. Now if this is a 2 by 3 matrix, right? This is a 2 by 3, 2 rows, 3 columns. So when I multiply the matrix A by another vector, it's got to be a 3 by 1, right? So it's all the vectors from R3, right? All the vectors from R3 such that A times X is the 0 vector from R3. In other words, right? In other words, we want to find all the vectors from R3, say with components x1, x2, x3, such that A, right, this matrix A times these vectors that I'm looking for, these vectors with 3 components here, is equal to, oh yeah, I'm sorry, this would be this would be from R2, right? The 0 vector from R2. I said R3 earlier. But I want to find all these vectors from R3 such that this product will be equal to the 0 vector. And do you see how it's just, solving a system again? Right. So we're solving for these x1, x2s, and x3s. Well, like we always do, or like I tend to do, like to do, with systems like this, matrix equations, I'll express it as an augmented matrix. Little bar for the equal sign, so you got matrix A over here, bar, and then just zeros over here. And very often the zeros aren't written because you just imagine that they're there. Because when you perform row operations, to put this thing into reduced echelon form, any column of zeros is going to stay a column of zeros. This will not change. So very often this isn't written, and you just imagine that it's there. Now, I already did this earlier in the video, this particular matrix. Right? So this in reduced echelon form looked like this. You had 1, 0 first column, 0, 1 second column, and then the third column was 53, negative 9. And again, the other side, that column of zeros, would stay a column of zeros. And again, we're just solving for this x1, x2, and x3 here. And remember, we look for our basic variables in free variables. So look for pivot columns, right? This first column is a pivot column. Second column, a pivot column. So, and these, would correspond to the coefficients of x1 and x2. So x1 and x2 would be our basic variables. All right, and then the third column is not a pivot column, right? The third column of this coefficient matrix, and that corresponds to coefficients of x3, right? So x3 is our free variable. Right. And what we're going to notice eventually, but I'll point it out right now, the number of free variables when you're solving this ax equals 0 equation, I'll tell you right now, the number of free variables you have will be equal to the dimension of the null space of the matrix. I'll just say the dimension of the null space, or the kernel. Right. I'll just point that out right now. Okay. Alright, well then let's go and let's actually solve this thing. Right. So again, x3 is free, which if you've seen me in other videos, I like to do this. Instead of using x3, I'll call it something, some other parameter that can take on any real number value. So suppose x3 is the variable t, where again t is any real number. Right, t is any real number. All right, well then from the first equation, we're seeing that x1 plus 53t equals 0. So x1 must be equal to negative 53t, right, for whatever my choice of t is. And from the second equation, right, we're seeing that x2 minus 9t, 9x3, must equal 0. Then I would solve for x2, add 9t. So x2 would equal 9t. And again, I already said x3 was just, t, right, just my free variable. And there we have it. This is a description of a parametric description of all the solutions of this ax equals the 0 vector. So, and now we have, the kernel. We have the null space. So the null space of this matrix A is made up of all these vectors. It's made up of every vector that looks like this. We have negative 53t as the first component, 9t as the second component, and then just plain old t as the third component. And these are vectors from R3, right? They have 3 components, but as long as t is a real number, just pick anything you want for t. Now, there's another way I could say this. Right? I mean, this is totally fine. This is totally valid. But like we did with the column space, I would like to express the null space as the span of some set of vectors, right? And then we'll find a basis for it and stuff like that. Remember how we did this earlier with free variables? I got the vector negative 53t, got 9t, got t. Right? This is the same thing as just pulling the t out of all those times the vector negative 53, 9, 1. Meaning that every vector in the null space of A, every vector that you can multiply A by to get the 0 vector, every single one of these vectors is a multiple of negative 53, 9, 1, that vector. So another way to state this is this. So the null space of A is just the span of the set with that one vector. This vector that everything in here is a multiple of. Right? The vector negative 53, 9, 1. So I'm going to put this in a brighter color because I like it better. Right? And we're going to do that with all these fundamental subspaces. We're going to express them as the span of some set of vectors. All right, and then you can check this out if you want. Take matrix A. Take this matrix we were given, and multiply it by this vector. You should get the 2 by 1 0 vector. All right, and check it out. First row times this. Dot product. You got negative 53 plus 45 is negative 8 plus 8 is 0. Then do the second row with this. You got positive 53 minus 54 is negative 1 plus 1 is 0. So this times this is 0. Great. So the negative 53, 9, and 1 belong in this null space. And any multiple of this, right, the span of this, any multiple of this will also make that equal the 0 vector when you multiply them. And you can check that out if you want. All right, and then we can see that, okay, every vector in here is a multiple of this vector here. So this one vector, the set with this one vector, the negative 53, 9, 1 that I have, this set is a basis for the null space of A, or the kernel of A. So we got that as well, coming from this. And a basis with, this basis has only one vector in it, and it's not the 0 vector. I remember, if it has the 0 vector in it, then it's dimension 0. If it's only the 0 vector, but this is a non-zero vector. So the dimension, right, the dimension of this null space is 1, right, because a basis has one vector in it. So we're getting all this stuff too coming out of this. Right? And this dimension of the null space is going to be given a name later. It's called the nullity of A, just like the dimension of the column space is going to be called the rank. But those will all come up in the next section. All right, but again, it came down to solving a system. You put your matrix on one side, column of zeros on the other, and solve for the 3 variables or 4 variables or whatever number of variables. And I'm telling you right now, the number of free variables you come across in this solution finding is going to be the dimension of the null space. See, there was only one free variable. The dimension of the null space was 1. And that's going to continue to happen. All right, that will always happen. All right, so let's go back here and they go take you through the same kind of thing here. All right, now this time, look, they're telling us here's a matrix A. They give you the reduced echelon form of A, right, this A prime, and ask you for a, what is the null space. So now this one I'll do real quickly. All right, I'll do very quickly on a piece of paper. All right, so here's the matrix A. They already put it in reduced echelon form for us, and like I said, I'm gonna make this into an augmented matrix. We're trying to figure out when this. This is a 3 by 4 matrix. So we're trying to find a 4 by 1, right? We're finding a x1, x2, x3, x4. Right? We're finding vectors like this, such that when I multiply A by these vectors, you get the 0 vector from R3, right? You get 3 zeros back. So I put the zeros on the other side of the bar here, and now it's already in reduced echelon form. The first column and third column have these leading ones, have these pivots, right? So x1 and the x3, those are the basic variables. And then the second column and fourth column are not pivot columns. So x2 and x4 are the free variables. All right. And like I said, I like to do this personally. So I'm going to have x2 be represented by s, and I'm going to have x4 be represented by t, where s and t are just any real number I wish. All right, you can leave them as x2 and x4 if you want. I just personally like using other parameters. All right, and then from the first equation, I'm seeing that x1 plus 3s, right, 3x2, minus 2t, right, minus 2x4 equals 0. So x1 would be negative 3s and then plus 2t. Now I already said x2 is just s, right? Then from the second equation, the second row, we'd be getting x3 plus 6t equals 0. So x3 would be negative 6t. Right, subtracting the 6t, 6x4. And then x4 was free, right? That was t. So the vectors are looking like this, right? These vectors x1, x2, x3, x4 I'm looking for are like this. So and you can split them up, right, based on the free variables. Right? Each of these vectors in the null space, each of these vectors that would make this matrix 0 when I multiply them would look like the following. You'd have s times negative 3, 1, 0, 0 plus t times 2, 0, negative 6, 1. Okay, bringing this down here. So, the null space of A, or the kernel of A, is just any linear combination of these two vectors. Another way to say that is the span of the set with those two vectors. Negative 3, 1, 0, 0. And 2, 0, negative 6, 1. And, again, this would be a subspace of R4, right? These are vectors from R4. And this set, right? This set with these two vectors would form a basis for this null space of A. Is a basis for the null space of A, or the kernel of A. And this basis has two vectors in it, two non-zero vectors. So the dimension of the null space of A, again later you're going to see this is called the nullity of A, is 2. And I said to you earlier, right? Remember, the dimension of the null space will be the number of free variables when you go through and try solving this AX equals 0 equation. All right? So pretty similar, just 2 free variables this time instead of 1. Now, if there are no free variables, I guess I'll point that out, as we haven't come across an example like that yet. If there are no free variables, then the null space of A will only be the 0 vector. Right? From whatever space you need it. Do you need it from R3 or R4 or R5, whatever. And then the dimension of the null space will be 0. Remember, the vector space with only the 0 vector in it is a 0-dimensional vector space. Right? So, we haven't come across any examples like this, but just know that it's out there. Right? You will come across matrices that, when you're going to solve A times x equals 0, the only value of x, the only vector x that'll make it true, is the 0 vector. Right? Now, the 0 vector will always make it true. It's just there are some times when it's the only one that'll make it true. Okay. All right. So a basis for the null space. Yeah, this was one of them. Right. Yeah, this was true, and then the span of those two vectors would be the null space. Right? The null space would be made up of any linear combination of these two. All right. Okay. Now again, I'll start the challenge activity here. You have a 3 by 6 matrix. So if V is in the null space of A, then V is in which of those Euclidean coordinate spaces are what? How many components would it have? Now I said this is a 3 by 6. The null space vectors are the vectors you would multiply this by to get the 0 vector in R3. So the vectors you'd multiply by would have to be a 6-component vector, right? It's a 3 by 6, you'd multiply it by a 6 by 1. So the vectors in the null space of this matrix would have 6 components. They'd be from R6. All right, so it's pretty simple, just entering a dimension there. Next question is, here's matrix A, 2 by 2. Here's some vector V, and they're asking you to multiply them. All right, so this is matrix multiplication to begin. So you have what, -8? No, that's +8 plus 8. That's 16 for the first component. And then second row with this be 24 plus 24 would be 48. And then is V in the null space of A? Is this vector in the null space of this matrix? No. Because to be in the null space, when you multiply by it, you're going to get the 0 vector. This is not the 0 vector. So, no. A very easy one there. All right, so again, basis for the null space. You're going to take this times some 2-component vector x, with x1 and x2. When's that equal to the 0 vector? 0, 0. Put it in reduced to echelon form, find your free variables, your basic variables, and solve. And then those solutions, right, what is a basis for those solutions? So I'll leave that to you. That's actually a lot more work than I want to do right now. I've already done it a couple times. And then what is formed by the null space of this matrix? Well, this is already in reduced echelon form. There are two pivot columns, right? So two basic variables, x2 and x3. The first column is not a pivot column, so x1 would be free. So one free variable, meaning the null space would have dimension 1. And remember, one-dimensional vector spaces are lines. Right? They're lines. And you have choices here. Now, because the first variable's free, right, that means the x value can be anything. Well, actually, no, x1 would need to be, no, x2 would need to be 0, x3 would need to be 0, and x1 can be anything. So that for or you think x, y, z. This is the x-axis here, but a one-dimensional vector space is a line. Okay. So now we talk about more to do with the null space and the solutions of a system. So this is all saying that if you have an m by n matrix and you have a system with a solution, so say a times x equals b has a solution called xp, some particular solution, then that solution will be the only solution, will be unique if the null space of A is only the zero vector. Right? If the null space of the matrix is only the zero vector, then if a system has a solution, it's going to have just that one solution. And you can read all this. So example here, I'll just read this one off and get to the next spaces. We're asked to determine if the solution of this system is unique. Again, just set up the system. This side, this on the left, little bar, then 1422 on the right. They don't even do the 1422 on the right. You can just put this matrix in reduced row echelon form and see, hey, if I was trying to if you were trying to find the null space of A, you see how the reduced echelon form of A has two free variables, two non-pivot columns? That means the null space of A would have a dimension of 2. So the null space of A would not be just the zero vector. There'd be more to it. So it wouldn't be unique. Right? Sure, the thing has a solution, right? A free variable. You could find solutions to the system, but there'd be infinitely many of them, right? Because you got the two free variables, right? If there were no free variables, there'd only be the one solution. So again, hopefully reading through that makes some sense. Like I said, I'm not really going to get into all that today. There's a section later where we go through more of this. So same deal here. If the null space is just the zero vector, then a solution might be unique. Might just be unique. Really, again, just set it up where this is on the left of a bar, this is on the right, and see if the system has one solution or more solutions or no solution. It's really that easy. And if it has just the one solution, then it's unique. Right? That's what it means to be unique. So I'll leave those to you. All right, but finally, now since we've already seen the column space of a matrix and the row space, the null space of a matrix, we've seen the column space and the null space. If you know how to find those two, these last two are pretty simple. All right. The row space of a matrix is just the column space of A transpose, right? Because remember, in A transpose, the columns of A transpose would just be the rows of A. All right. So if you just take the transpose, and I'll show you an example, of course. You just take an example, take a matrix, take its transpose, and find the column space of the transpose. you'll then have what's called the row space of the original matrix. And the same thing goes for this other vector, the fourth of these fundamental vector spaces, the left null space of a matrix, or the left kernel. Now notice how it's called the null space of A transpose. It's again very simple. Just look at A transpose and find the null space of A transpose. So again, you've already seen how to find the column space. You've already seen how to find the null space. So now for this row space of a matrix and left null space of a matrix, you're just doing the same thing, but for the transpose of that matrix. All right, so let's take a look. Right, so they gave us this, again, this same matrix, and I'll write it on paper, and we'll find the row space and the left null space of this matrix. Okay. So again, they say, let's find the row space. Now, just like column space, right? The row space is just all the linear combinations of the rows. So the row space of this matrix would be the span of the vectors, 1, 5, 8, and you can write them as rows, write them as columns, whatever, right? But there's the first row, right? Again, I'm writing the rows as columns, but these are the rows of A, written as columns. And you're going to see that they're going to write them as columns. I think it's mostly to save space, because if I keep writing the rows across, it's going to be really long. I think they're just doing it to save space. And then the other row, -1, -6, 1. That's the row space of A. All right. Now the question is, do I need all of these vectors? Is every linear combination of these two enough, right? Or can I get rid of one of them? So are these vectors independent? Now you can tell right away that they're independent, right? Because remember, if there's only two of them, then they'll be independent when they're not scalar multiples of one another, and these are not. So this is going to end up being okay, and this is a subspace of R3, right? All the vectors, all these row vectors from A have three components. So the row space of A is going to be a subspace of R3. All right, now let's actually figure this out. Is this correct here? Remember, the row space of A, another way to find it would be, what's the column space of A transpose? So we look at A transpose. Remember, A transpose, this is the original is a 2 by 3. So this is going to be a 3 by 2. And the first row becomes, the first column of the transpose. The second row becomes the second column of the transpose. And then I put this, just like you would find the column space of any matrix from earlier in the video, earlier in the section, put this into reduced row echelon form. Now, I'm going to refresh your memory, hopefully. Remember on the calculator, when the number of rows is greater than the number of columns, your calculator comes up with an error. If I'm doing a 3 by 2, and go 1, -1, 5, -6, 8, 1. Alright, remember, when the number of rows is greater than the number of columns and you try to go reduce row echelon form, it comes back with an error. It says invalid dimensions. Oh, sorry, I didn't have the calculator up. But it comes back with this error, saying invalid dimensions. So how do I fix that? So remember, I did this before, I believe, in previous videos. So right now it's a 3 by 2. Just add on columns of zeros until the number of rows and columns are the same. So I'm just going to make this a 3 by 3, and then you see how it pops on this column of zeros, and just ignore that column of zeros. Just ignore it. And get out of here, go reduced echelon form again, and again, just ignoring that last column of zeros, and we get this. And look for my pivot columns, right? The first column is a pivot column, the second column has a pivot. So that means the first column of the original matrix is part of a basis, and then the second column also. So this set with 1, 5, 8 and -1, -6, 1, that is a basis for this row space, right? Or you could also say the column space of the transpose. But the column space of the transpose is the same as the row space of the original. So this set here forms a basis for the row space, this set with these two vectors, 1, 5, 8, -1, -6, 1. And therefore, the dimension of the row space would be 2. Right. Two-dimensional space, a plane. All right, now let's find the left null space of this same matrix. Right. Say we're asked to find now the left null space. Right, not just the null space, but the left null space of A. Now, this is denoted as the null space of A transpose. So even in the notation, they're kind of telling you what to do. So just look at A transpose again. And, this is a 3 by 2. So we need to find vectors that are 2 by 1. Right? We need to find x1 and x2. Again, I'll call this vector x here, such that A transpose here times x is equal to the 0 vector. And this will be the R3 0 vector with 3 components. So I set up, basically I'm setting up this system, right? This augmented matrix. And I've basically already done this. I put this in reduced row echelon form already on the calculator. This would look like this. We saw this earlier. 1, 0, 0, 0, 1, 0. A little bar for the equal signs, and then 0, 0, 0. And you see how there are no free variables this time? All right. Again, the first column, second column, these are pivots, so x1 and x2 are basic, and there are no free variables, no non-pivot columns. And from that first row, you're seeing x1 has to be 0. The second row, x2 has to be 0. So this null space of A transpose, or what's called the left null space of A, is just the set with the 0 vector. Right? Is just the set with the vector 0, 0 in it. And therefore it has no basis. It has no basis and dimension 0. Right, all that stuff would be true as well. Right. If you're again, the vector space with just the 0 vector in it has no basis or an undefined basis and a dimension of 0. Right? Yeah, and it's really that simple. If you know how to find the column space of a matrix, if you know how to find the null space of a matrix, just look at the transpose when you're asked about the row space and the left null space. All right, so then for the row space, just look at the transpose, put it in reduced row echelon form, find the column space of A transpose, and that'll be exactly the same as the row space of A. And then for this left null space of A, again, go do the transpose and find the null space of the transpose, and that'll be the left null space of A. All right. So you can read through all this stuff here. And they do the same thing with you here. I'm just gonna leave these to you. Alright, I've already shown you how to find the column space, the null space of matrices. And then you got, challenge activity 4 levels here. I'm gonna leave this stuff to you. These are pretty similar to the challenge activities from earlier related to the column space and the null space, but now for this row space and left null space. You see how they're all tied together? Now, one other thing I can say that they're saying here is that the row space of A can also be found using the echelon form of A called A prime, because the row space of A is equal to the row space of A prime. So if you'd like, and again, you don't need to do this, but if you're, now this is for the row space only. Alright, this is for the row space only. If you're given a matrix and you're asked for the row space, you can put it in echelon form or reduced echelon form, and then any rows that have a pivot in the echelon form will form a basis for the row space of the original matrix. And that's what they're going through all here. So you see, here's matrix A. They just put it in reduced echelon form, and you see 1 0 0 0 1 0 0 0 1, those rows with pivots in it. Those three, 1 0 0 0 1 0 0 0 1, those three vectors do form a basis for the row space. And you can do that. It's simple. You don't have to look at the transpose if you want. Okay. Again, another basis is these here, which consists of the rows that correspond to the pivot rows of A, but you can use those pivot rows as a basis as well. That's all this last part's on. All right. Again, this is only for the row space. This is only for the row space of a matrix. Can you keep the pivot rows? The column space, right, you couldn't keep the pivot columns. You had to use the columns from the original matrix that corresponded to the pivot columns. All right. So just be careful. All right, again, they have you doing this here. So again, matrix here, nice 4x5, put in reduced echelon form. And they're asking for a basis for the row space. Now the row space should have vectors with 5 components, right? These vectors only have 4 components, so that can't possibly be a basis for the row space of A. But I can give you a basis by looking at these pivot rows, right? The rows with the leading ones in it. Just so these first 3 rows, 1 0 0 negative 2 3, the 0 1 0 negative 1 0. And 0 0 1 1 0, those form a basis. And you see these 3 vectors here. Those would form a basis for the row space. Right. So again, this is only for row space. And in fact, I would say, they put it at the end here because it's a little different than what you've seen. I would recommend keeping matrix A the way it is, putting it in reduced echelon form, then stating the column space and the null space of A. And then I would look at the transpose of A, put that in reduced echelon form, and then tell me the column space of A transpose and the null space of A transpose, which in turn will be the row space of A and the left null space of A. Right? So I would recommend doing all that, just so you keep things in a nice order. Alright, then you have your additional exercises. Again, some of these are on your assignment, some are not. I would still recommend looking at all of them, and you can also take a look at the solutions when you're struggling, but please don't look at the solutions first, right? Try to work out the problem on your own first, and then look at the solutions. And of course, if you have any questions, send them my way in the Canvas inbox, and I'll get back to you as soon as I possibly can, of course. And thank you very much for watching.